Okay, so, well, what we're going to be doing is talking about heat formulas. So what I kind of want to get really into us looking at is understanding that you are going to be calculating when you use M times C times change of T, that you are finding the Q surrounding. And so if it is asking you for the Q of a system, these signs must change. So not only in this lab and in the next lab, your 12 and 13 lab, are these sig figs going to count, but these signs are going to count. If you flip sign, I'm going to have to take off tons of points because it's actually very incorrect. So please, please, please focus. Did I find Q surrounding or did I find Q system? You were usually calculating Q surrounding. So just look at the question as, is it asking me for that or is it asking me for Q system? Okay? Because the signs are opposite. What I mean by that is, like for the Q surrounding, you get negative 22. Then the Q of the system would be negative 1 times negative 22. So the Q of the system would be positive 22. Okay? And the other one we're going to look at is the change of heat. So you're going to take your Q system, you're going to divide it by the moles of the reactant or product. Okay? The other things to look for is that we're going to be using the density of water to find that for solutions. That includes hydrochloric acid and sodium hydroxide. We're going to be using the specific heat of water. And then the change of temperature you were going to get either from the temperature probe of the graphs that you recorded in 13 or that of what you're recording in our lab 12. Okay, again, really take a minute, even pause the video to look this through. I'm not going to go through it because you all can read, but understanding that when we have an endothermic reaction, that is when heat is going into the system because the system itself is cold. And so that means heat from the surroundings has to go in. So in all of these reactions, heat is going to the colder place. Heat dissipates. It doesn't like to stay where it is because heat is when molecules move quicker. And and they hit each other and they don't like that. So they'd rather move to something colder to slow down, have less energy, relax, as we can all, I'm sure, relate to. And so the same thing in this instance. And so with endothermic reactions, it's the idea that the actual reaction itself is cold. And so the heat of the surroundings goes in, making them feel colder, right? Because they're going to be room temperature. But if all of that room temperature heat goes into the reaction, it's going to feel colder. Same thing with exothermic reactions, but reversed. Now that the reaction itself that's going on is hotter, and so that heat is going to go into the surroundings, making it feel warmer. Okay? So that is what this entire chart is trying to get us thinking about. Is it that this reaction happening is going to be cold, and so that means that the heat is going to go in? Or does it mean that the reaction itself was hot, and so that heat is going to go into the surroundings? Okay, and that's why it says reaction system lost energy, because whenever you have heat going out, heat is energy. Temperature measures heat. Okay, all right. So calculations that we're going to look at. So the one thing I want to run through here is basically take it in steps. Find out how much of a solid did you add. You're going to convert the volume of water to a mass. So you're going to use, again, that 1 gram per milliliter. So if we take that 50 times 1, we're going to cross out our milliliters here. And if we do that, then that means that, let me grab a pen so we can do that. So if I just cross these through, then that means we get grams left. So we get 2.038 plus 50, which if we're doing sig figs, because there's only 3 here, it means there can only be 3 here. And that's what we've done. And then finally, we take the temperature difference, which from all of your graphs is just going to be what was initial, or what is final minus what was initial, okay? So it's always T final, in this case, minus that T initial. This is, again, important because if you flip them around, then this sign would be different, and that means your overall sign will be different. So please, please, please take note. It is T final minus T initial. Once we find that change in heat, we're going to multiply it by the specific heat of water. Please use this. You're going to use it also in parts 2 and 3 of the 13 lab and also in 12. And you're going to get this. in joules, and that's great. And it's best to convert it, again, sig figs. We only have 2 sig figs because of our change in temperature. I lost it for a minute, I found it. So we've got to convert it here. You want to get full points, that's how you do it. And again, this was calculating the heat change of the surroundings. I have a typo, I'm just going to delete it now. There we go, you didn't see it. And it's the Q of the surroundings, but I want to know the heat change of the system. And so that means that because I have a negative surrounding, I'm then going to have a positive system. Okay? Finally, what I'm going to do is calculate the amount that reacted. And that's simple. I think that when we see a lot of numbers, we get really anxious, right? It's a lot of stuff. But what's really nice is when we do have a lot of numbers, it means they're giving us a lot of answers. Either it means they're giving us extra information that we don't need and we can throw out, or it means it's giving us some other information. So don't ever freak out if you've got, you're given all of this information. So what we've got is the amount of ammonium nitrate, and I knew that I had this many grams, right? Because we're given that many grams, and you're going to find in your lab you weigh out that many grams, and you're going to multiply it by the molar mass, which is what you get from your periodic table. Right? So you have 2 nitrogens, 4 hydrogens, and 3 oxygens. And you're just going to add those all together. This is going to get rid of my grams, right? So then we're left with moles. And that means that when I take this divided by 80, I get this many moles. The way I then convert that to change in heat of the system is I'm going to take my joules here. I'm going to convert that to kilojoules, which means I'm going to divide it by 1,000. So if I take this and I divide it by 1,000, I'm going to get kilojoules, which is good, which is what we get here. That's positive 0.65, positive because we are the Q of the system, not the surroundings, but the system. And I divide that by the number of moles that I got. Remember, I got those moles by simply taking the amount that I weighed out and or were given, but in this case weighed out, and I divide it by its molar mass. And by doing that, I will get the moles, and that gives me the heat of the system. All right. The other way to look at this, so in that case, we found out that was an endothermic reaction, right? Because we had a negative Q surrounding, but a positive system. So the other way to look at it is, what if we have a positive surrounding and a negative system, aka an exothermic reaction? And so let's look at the solutions. The only thing about the solutions that's different, don't panic, is that instead we're given 2 things, right? We're not given a solid, we're given solutions. But these work just the same as they did with that water, right? We had 50 milliliters of water, we have 50 milliliters of all of these things. And so again, we use our wonderful 1 gram per 1 milliliter, that density, and we're able to then convert these all to grams. And so in this case, I've just added them together, and that gives me my total for the solution, right? Because if we have a solution, it means that we have 2 things. So both have to be in there. And then I just do the same as I did before. We're gonna use the specific heat capacity of water, just because the NaOH and the HCl, to be 1 molar, are gonna be dissolved in water. I know that makes no sense, so I'm not gonna go into that too much. Just know it's okay to use the C that you've used before and use in future unless told otherwise. And you're going to use that specific heat capacity of that 4.18 here. I'm sorry, my 4 looks so weird. That 4.18. And then you're going to take the change in T. What they did is whatever answer they got, they divided by 1,000 like we did before to get kilojoules. And again, we just took that sign. Notice it's positive for our surroundings. So then it's going to be negative. I'm sorry, I'm circling over the number for our system. Okay, and then this is how we do that, right? I want to get to the actual stuff, so we need the moles. So I don't know why I did air quotes, but you need moles. The same idea again, grams. We use the density, and then we need to get it to moles per liter, right? Because we remember that these are 1 molar. So if I have 1 molar, it means that to get to moles, I need to get first to liters, because that's what this 1 M means, is mole per liter. So I'm going to first get this back to liters by going to milliliters, which is what I did before. And then I'm going to take that, divide it by 1,000, and then multiply by 1, and I'm going to get my moles. Great. Notice we have equal amounts. That means they're going to neutralize really well, because it's the same thing for our sodium hydroxide. And then what we're going to do is it says, what's the heat change per mole? So I have my moles of HCl, and I multiplied that by my 1-to-1 ratio here. And because of that, it means that the heat system is going to be the same, because again, like I said, it's equal amounts of HCl and NaOH. So we just take HCl. This is how many moles of water we have because of the 1-to-1 ratio. I take my heat change of the system, right? If we go all the way back, our system, it's negative now because we are exothermic. Start boggling those around in our brain, making those connections. So I take that, I divide it by the moles, and I get the answer, negative 61 kilojoules per mole of water, okay? Because they're in equal amounts, sodium hydroxide and HCl. The final thing I want to put in here, in case you got to the end of this video, is please dress properly for lab when you come in. No open back, knit, or baggy sleeve stuff. I know it's tempting because it's freezing, but please do not. Also, please, I know you guys like joggers, but they need to cover your ankles and your shins. All right, those have to be covered. My ankle is not covered, so I just shoop, okay? And now I am covered. I don't know if I'm on camera, but covered. No frayed sweatpants because they're a tripping hazard and we have acid, okay? Don't want anyone tripping, knocking acid onto anybody. And again, no ankles showing. It's okay to have, a slightly, like, this is okay as long as you keep things able to be in your person, okay? Because the last thing you want is this getting so baggy that it dips in some acid and you don't realize until it's, eating at your skin. Okay, that's the only thing. This does not save you either. Don't think that, it'd be better that way. And finally, please wear basic long sleeve shirts or t-shirts as well. All right. Thank you very much, and I'll see you guys on Tuesday. I'm just going to discard all of those.